we know that we need kilograms at the end, so clearly we're going to need to multiply this fraction by cubic meters in order to divide out those two pieces and just be left with kilograms. Alright, so how do we figure out the volume of this particular rod? Well, again, if we just look at one single sliver or one single coin that's been chopped out of it, then the let's back up, infinitesimal volume is going to be given by a infinitesimal cylinder. And again, so this is D capital V for volume, is going to be equal to the area, so pi r squared, of one of these ends multiplied by the height, which is going to be the distance across, which we know is going to be dx. Now, if the rod itself is uniform going all the way across with the exception of the density, then this does mean that the volume as we go across dv dx is going to be constant. So there is no change in volume as we go all the way across. The change comes in the density itself. Somebody might be confused about how this might happen. If, for instance, a rod is created vertically and let's say, molten steel is poured into a mold vertically, then potentially any heavier density materials will eventually sink to the bottom. As long as it's kept at a high enough temperature for long enough, it will eventually have the higher density stuff sink to the bottom all the way, and the lower density stuff float to the top all the way. So there will be a clear delineation between like low density and high density, or there will be a region where it's sort of muddled a little bit, but the heavier density stuff will definitely be all the way at the bottom, and the lighter density stuff will be all the way at the top. And then somewhere in the middle, they kind of begin merging. So it would not necessarily be a nice linear function, as some of the examples say. So if it is a density function that is given by some sort of function rho, it could very well be just about anything. Alright, so mass is going to be equal to volume, which in this case we already figured out the infinitesimal, but if we want the no, that's fine. I'm doing alright, I promise. It's fine. Alright, so the mass of one segment is going to be given by... Are they just doing... Okay. Rho at x times... Okay, yeah. So I think basically what they're doing here is they're saying, you know, it's a thin rod, so we don't even need to think about necessarily the shape of this thing. It doesn't need to be technically a cylinder. It could be literally any shape we want. So what they're doing is they're saying just take that volume and we're going to let that be we're just going to let that be dx. Due to the fact that it's an infinitesimal, or because you can say, oh, it's a thin rod, it doesn't really matter how big it is, then our m is going to be given by rho x dx, and then we're going to integrate over the entire distance. Alright, so they're basically treating it as a one-dimensional object. And again, we don't actually need this stuff. Okay, so it's essentially a one-dimensional object. So if we had something that was, let's say 3 meters long and variable density, given by the density function, rho of x is equal to let's do x sine of x. Alright, so then we want to find the mass of this object. That's behind my head, isn't it? Totally. Oh, almost. All right, we made it. So the mass here is going to be given by the integral from 0 to 3 of x sin x dx. Then here we're going to need to use integration by parts again to solve this integral. So again, we have x is just going to be u, and dv is going to be sine of x dx. Therefore, v is going to be the integral of sine of x dx is negative cosine of x, and du is just equal to dx. All right, so then an integral of u dv is going to be equal to uv minus the integral of v du. So here we end up with uv is going to be negative x cosine x evaluated from 0 to 3 minus v du is just going to be cosine of x dx integral from 0 to 3. So integral, no, sorry, that was already done. So here we have negative 3 cosine of 3 minus a negative is a plus, so it's going to be 0 cosine of 0. So this is all going to be 0 thanks to the 0 out front. Negative 3 cosine of 3 is going to be a negative number, so a negative cosine of 3 is going to be a positive number times 3, so that's nice. All right, and then over here, the integral of a cosine of x dx is going to be a sine of x dx. It's going to be minus sine x dx. Nope. Just the sine of x, evaluated from 0 to 3. Okay, minus the sine of 3 plus the sine of 0. So that's also 0 there. The sine of 3 is going to be a very small number because 3 is very close to pi. And that means that our y distance very close to pi is also very close to 0. So that way, around your unit circle going that way. That also means that the cosine of 3 is going to be a large negative number, so close to 1 or close to negative 1. And then when we multiply by negative 3, it's going to be fairly close to positive 3. So positive 3-ish minus something very small. We're going to get like 2.7, somewhere in that neighborhood. Oh, no, it's in degrees. Of course it is. Radians. 3 negative times 3 equals we go. So that is a 2.9699774, and then if we subtract 3, sine of that is 0.1411 is equal to, okay, this is going to be approximated by 2.82889. And if we assume that this is going to be in kilograms, then that's how that all works. Okay, so this would be kilograms per cubic meter. And again, depending on how accurate you need this to be, make sure you round appropriately. The next kind of density function that you can have is one that is dependent upon where you are on a circle. So specifically, it is radial. So your density is telling you how large is this thing going to be, or sorry, how dense is this going to be along the entire radius of a circle. So you have some sort of disk that is telling you how big this is, how heavy it is at any given point, how dense it is at any given point. Well, at this point, we can kind of do the same thing that we did with the washer method, where you cut a particular location, and then you're going to say, like, oh, well, this is going to go all the way around the circle, like this. The mass for this particular like washer that's going all the way around is going to be equal to, so in this particular case, it's kind of like you need the area times the density at that particular point. So the area of this washer is very much like the yep. Okay, so they're saying that we can also use this to find the average radius of this particular washer. So basically we're calculating the radius at this particular point, x star or x sub I star, or whatever you want to call it. The area at any given particular x sub I is going to be pi times x sub I squared plus, minus pi times x sub I minus 1 squared. It's pi times x sub I squared minus x sub I minus 1 squared. This was then x sub I plus x sub I minus 1 times x sub I minus x sub I minus 1. X sub I minus x sub I minus 1 is delta x. x sub I plus x sub I plus, minus 1 is going to be really, really close to some twice x sub I star. Because these are infinitesimally close to each other, it doesn't actually technically matter which point you pick in between those two endpoints, but the easiest way to do it is just to average the two out, and it ends up being like, okay, well, if you add the two endpoints, it's going to be more or less the same as if you add two center points. And again, if it's infinitesimal, it technically doesn't even matter. So a sub I is going to be equal to pi times 2 x sub I star times delta x okay, and then from here the mass is just going to be that area that we just found multiplied by the density at that particular point, which again we're just using x sub I star for that. So any given m sub I is going to be equal to a sub I times rho sub I. So 2 pi x sub I star delta x, and even we can back that off. So this is going to be rho at same x sub I star times delta x. And then if we want to do this for real, we got to say, okay, we're going to sum up all these things, and when you sum up all these things from A to B, it's going to end up giving you, and when we try to shrink down the delta x to 0. So when we take the limit as delta x approaches 0, that is when we get an actual integral over this thing. So the true mass of the entire disk it's going to be 2 pi integrated from 0 to the radius of this thing of x times rho of x dx. Alright, there is kind of a classical problem that I use all the time, or used to use all the time in this class. We're trying to pump water from out of a tank through a hose, and doesn't technically matter where the hose is in all of this. Most of the time what we would do is we'd say, like, okay, you're gonna get, come on now, there we go. You're gonna get some sort of hose which then takes the water from the bottom and then runs it along the side and exits out at, say, ground level. Now you have water in the tank. And it's being pumped down through the bottom. Which takes basically no pressure at all at this point, because the water here, the water pressure is pushing down on the rest of the water underneath it, which is then going to cause all of the rest of this water that's at the bottom to come out of the hose and get sent out just by using gravity. Hey, Matthew. So it's very easy to do this first amount of work. Yeah, right. I missed my Monday morning math. So, you know, kids were a little busy. Couldn't really just leave my daughter alone for 2 hours. I mean, she's old enough. She could have handled it. But, like, you know, that's not nice. Last Monday, they had both had something else to do, and they were perfectly happy to leave me alone. And I'm like, okay. But this week, nah, not so much. Yeah. Occasionally they do love neglecting their old man. Anyway, I need a lot of love and attention. Which one was that? Not that you have either. Alright, that's fair. Oh, yeah, yeah. Learning styles, yep. So, I mean, I've sort of known for a while about it, right? Like, I took education courses and things like that. So we did learn learning styles at some point, and we've done training on it, things like that. And Derek's final conclusion, which, I mean, I'm going to ruin the video for you, but it's always good to hear him say it anyway. So Derek's final conclusion is that it's not one like learning style that you prefer or anything like that. It doesn't really work that way, and he proves it by doing a quick little like let's see how many of these you can get right just by me like listing out all of the objects that are in a stack of cards. So, you know, it's like flashcards. So he says what the things are in the list, and the people have to repeat back as many as they can out of 10. Just saying the things, then them trying to rattle them off didn't work very well. So everybody's like, oh, well, auditory learning is terrible. And he then showed the pictures of all of them, and then asked them to do it again, and everybody scored higher. So like everybody is a visual learner apparently. But then he's like, but that's not really how this works, because you're not, you know, you don't have one mode where everything comes in. And so he said, watch this. And he changed it up for the third one, or later on, and it like, it has the word, it has the picture, and he says it out loud. All three at once, and almost every person got 10 out of 10. So it's not a matter of like getting the one learning style which works for you. It's a matter of using multimedia in order to reach your audience in the best way possible. So for instance, I should be turning on captions. The only reason I'm not necessarily doing that is because I'm still pretty new at all of this, and yeah, I want to fix that. Yes, so the, multimedia is really the point of all of this. Get stuff that is written, get stuff that is heard, get stuff that is seen, and um, and not just like a word, but oh yes, it's very anti-minimalist. So like I could write out the problem here for this, like how much work is done given a pump is pumping water from a tank, cylindrical tank, out of a hose that is at this particular height and all this stuff. And I could list out all the, pieces of information for this problem. And this is really kind of where a lot of us in terms of education say like, oh, well, the student needs to learn some of this too, is a lot of times we try to tell them to draw a picture first whenever you're trying to solve a particular problem. So in that particular case, honestly, we don't give them a picture, at least not for an exam or something like that. We'll tell them that, I do this in class a lot, is like, I will give a problem, I will say it out loud, I will write it on the board or whatever, but it's just going to be the information, and then say, how do you do this? And invariably, the first thing that you should do is draw a picture. And like I always tell my students, step one, draw a picture. And so we'll do it in class and say like, here's how to draw this particular picture. Yeah, and you have to bring it back to your personal experience. So if you've never, if you've never seen a hot water tank in the basement of your house,